Hello, students. Welcome back to the new session. So here we are going to discuss Hall effect and current sensor. So two sensors we shall discuss today and complete them. In last class, we have seen the magnetic sensors. In next class, we shall see the heading type sensors. So we are here now. We have completed these topics, and now we are going to complete Hall effect and the current sensor. So first one, current sensor we shall discuss. It is eddy current sensor, also a type of current sensor only. So eddy current sensors are non-contact devices capable of high resolution measurement of position and or change of position of any conductive target. So eddy current sensors are also called inductive type sensors, but generally eddy current refers to precision displacement instruments or non-destructive testing probes, and inductive refers to inexpensive proximity switches. If these are also proximity switches or non-contact type sensors. High resolution and tolerance of dirty environments make eddy current sensors indispensable in today's modern industrial operations. So this is the construction of eddy current sensor, and here the object is essentially should be a conductor. It should be a conducting material, and when the alternating current is applied to this probe, so here in the presence of this conductor, the magnetic field will induce. So that will carry that will carry the localized electric currents. So now localized electric currents will be induced in this magnetic field, and now this gap should be maintained with appropriate distance. And here this is LC circuit. LC is it is the oscillation circuit, LC oscillation circuit, or it is also known as oscillator. So this selects the frequency, right? It selects the correct frequency, and then that is evaluated by a signal evaluator, and you have a switching amplifier. These are the three components which are used in constructing this eddy current sensor. The construction is very simple, only three elements, and it can identify, or it can recognize the conducting type materials. So essentially the target should be a conductor. So eddy current sensors are used to detect conductive materials. They comprise of coil. They comprise of a coil, an oscillator, a detector, and a triggering circuit. When an AC is passed through this coil, an alternating magnetic field is generated. If a metal object comes in close with the coil, then eddy currents are induced in the object due to the magnetic field. These eddy currents create their own magnetic field, which distorts the magnetic field responsible for their generation. Impedance of coil changes, and so amplitude of alternating current. This is used to trigger a switch at some predetermined level of change in current. So eddy current sensors are relatively inexpensive, available in small in size, highly reliable, and have high sensitivity for all displacements. So that is the eddy current special feature. Advantages of eddy current: tolerance of dirty environments, not sensitive to material in the gap between probe and target, less expensive and much smaller than laser interferometers, less expensive than capacitive sensor. And disadvantages: not a good choice in these conditions, extremely high resolution, capacitive sensors are ideal, large gap between sensor and target is required, so the gap should be with appropriate distance should be maintained. Optical and laser are better in this case. Applications of eddy current sensor: automation requiring precision location, machine tool monitoring, final assembly of precision equipment such as disk drives, drive shaft monitoring, vibration measurements. Hall effect sensor. Next type of sensor is Hall effect sensor, a device which converts magnetic or magnetically encoded information into electrical signals. It is also a type of induced type, inductor type. A Hall effect device is a solid state device and is a passive transducer. It requires external source. Even eddy current sensor is also a passive type transducer. Magnetic field has two important characteristics: flux density and polarity, north and south poles. So the output signal from Hall effect sensor is the function of magnetic field density around the device. When the magnetic flux density around the sensor exceeds a certain preset threshold, the sensor detects it and generates an output voltage called Hall voltage. So this is from the diagram, it will be more clear. So this is the working principle, and this is the slab, and here it is a p-type semiconductor Hall element, and now the supply is given to the slab at these two terminals. At the terminals, when there is no magnetic field, there will be these charge carriers will pass in the straight line. Now the south pole of the magnet is brought nearer to the slab, then this will be diffused. These electron hole pairs are diffused and they will reach these edges. So when you measure with a multimeter or any volt measuring device, when you measure across these two terminals, then you will be getting a voltage that is known as Hall voltage. So this is the working principle and very simple in construction. So essentially, the south pole should be nearer towards this p-type semiconductor Hall element. So north pole you cannot keep here. Only south pole will act, and the lines of force will be forming between north and south poles. So this is the simple construction. And the Hall effect sensor consists of a thin piece of rectangular p-type semiconductor material. So these materials are used: gallium arsenide, indium antimonide, and indium arsenide. These are the three materials. When the device is placed within a magnetic field, the magnetic flux lines exert a force on the semiconductor material which deflects the charge carriers, electrons and holes to either side of the semiconductor slab. So, those are diffused. This movement of charge carriers is a result of the magnetic force they experience passing through the semiconductor material. Advantages: production of an high that is voltage output voltage signal independent of the rate of the detected field. All effect sensors display low carrier density, hence conductivity is smaller and their voltage is larger. A high speed operation is possible. All sensors can measure zero speed also. Disadvantages: the Hall effect sensor is not capable of measuring a current flow at a distance greater than 10 centimeter, possible for external magnetic fields to interfere with the magnetic field and bias the measurement of current flow. Even the with other environmental factors plays a role here. Temperature affects the electrical resistance of the element and the mobility of majority carriers, and also the sensitivity of Hall effect sensors. The offset voltage exists as an output voltage in the absence of magnetic field. Applications of Hall effect sensors: current sensing, variable speed drives, motor control, protection indicators, power supply sensing, motion sensing, diaphragm pressure gauge, flow meters. So these are the major applications of Hall effect sensors. And in heading sensors also Hall effect concept is used. And these are the applications, advantages, disadvantages. So far we have seen the current sensor as well as Hall effect sensor. There ends these two sensors. In next class, we are going to discuss the heading sensors. These are the books, textbooks, and these are the e-resources. And thank you, students. We stop here. In next session, we will commence the heating sensors. Thank you, students.